It's really a great pleasure to be here today. It feels like home, although now it's been about over 10 years since I was here last, so it's been quite a while. What I'd like to share with you today is our work in thinking about how we can take advantage of nano-engineered materials in a way to create new functionalities such that we can advance energy and water technologies. Many of you are probably familiar with this pie chart already and think about in the US how much energy we're consuming, in particular and what we rely on as our energy sources. For example, you see that coal, natural gas, and petroleum still dictate most of the supply. And certainly it's very useful in thinking about kind of the opportunities that we need this kind of energy supply for such things such as residential and commercial buildings, that of transportation systems, and various industrial processes. And so while certainly there's a lot of need in the developing and developed worlds for a lot of these kinds of energy technologies, the challenge is, of course, that they emit greenhouse gases and that we need to think about new approaches such that we can mitigate climate change, which certainly is a problem that we're facing readily now. And I think now there's really an ultimate opportunity space and thinking about kind of the advent of new kind of engineered kind of materials and structures. And so a lot of my work has been really focused on kind of this intersection point, in particular thinking about kind of how we can take advantage of these new functionalities of materials, such as, say, the extraordinary properties, electrical, mechanical, or thermal properties of new materials, such as that we can manipulate such things as light, that of wetting and kind of fouling resistance of structures, for example, CO2 capture, and that of energy conversion and storage. So certainly there is a breadth of opportunities in this space and thinking about how we can take advantage of new nanotechnology. What we've been focused on, a lot of the work has been thinking about kind of thermal-based solutions, where we look at the intersection of these materials with heat and mass transport in particular. And we think that then in thinking about this problem, when we can take advantage of these various materials with functionalities, then we can start to address larger scale problems, say that in the space of kind of solar thermal, that of photovoltaic cells, that even that at the intersection of water, right? And thinking about, well, how can we now produce water that's sustainable for the world? So what I thought I'd do today is share with you some of our work and thinking about this particular opportunity space and looking at, well, the fact that while certainly where the energy sources that we use right now are that of coal, natural gas, and petroleum, and the renewable market is still very small. It's about 10% of the total amount of energy that we can use and deploy. And even within that kind of renewable range, we see that, in fact, solar, which is only about 6% of that 10% in renewable. And there's certainly a significant opportunity when we think about sunlight and the abundance of sunlight that we have. So certainly solar energy is underutilized at this point. And a lot of our work has been recently thinking about how we can develop more efficient and kind of lower cost solutions such that we can make solar energy utilization more viable in the long run. So when we think about solar, certainly what comes up in our head is often solar photovoltaics or PV cells, right? And the idea here is that you can take advantage of photoelectric conversion of the partial solar spectrum of the sun. And the way you do that is that you kind of utilize these photons to generate electron hole pairs, and then that allows you to produce electricity. It's really nice in the fact that it's become relatively low cost in nature, and it's solid state. So it's pretty simple in the design, and it can be relatively scalable. So certainly you've heard a lot about this, and a lot of people are deploying them in their homes, for example, as well. In contrast to that, the other type of technology that has been kind of researched and developed in the past, say, decades now, is that of solar thermal systems. And the idea here is that you harness the entire solar spectrum in the form of heat. And in this way, then you heat up, say, a working fluid, say, for example, in this parabolic trough type configuration, and then it drives a traditional, more steam cycle. Okay. The advantage of this is that it can be potentially continuous if you can integrate it with storage, which is relatively cheap. Thermal storage can be relatively lower cost than that, say, of batteries. And so there is a lot of opportunity in thinking about, well, how can we now take advantage now of the full spectrum rather than the partial spectrum of that of photovoltaic cells and utilize them in this way. What my group has been working on for some time is kind of a hybrid approach with the combination of photovoltaics and solar thermal processes. And this is known as solar thermophotovoltaics, or otherwise called STPVs. And the idea here is we want to really take advantage of both kinds of approaches, where we can harness a full spectrum of the sun, allow for continuous operation with storage, and allow it to be also solid state and scalable. Right? And so what we do here in a solar thermophotovoltaic conversion process is that you kind of have an intermediate kind of selective absorber emitter structure. So the idea here is that now you have the sunlight that converts a broadband solar spectrum to a narrowly tuned thermal emission via this selective absorber emitter structure that's tailored to the band gap of this photovoltaic cell. And in this way, because you're tailoring this thermal emission process, you can effectively get, theoretically, efficiencies greater than about 80% or so. Right? So this is much higher than the well-known Shockley-Queisser limit that people know for single-junction PV cells. And so there certainly has been a lot of interest in thinking about, well, how can we take advantage of these STPVs and realize them if the theoretical efficiencies are extremely high? Certainly, while it sounds kind of straightforward in nature, where you can kind of tune the broadband solar spectrum to a narrow band, there are certainly many challenges. And so for the past 5 years or so, my group has been working on these STPV type technologies and being able to take advantage of nanophotonics as a way in collaboration with my a couple of faculty members in physics, Martin Solacek's group in Department of Physics, and then also Ivan Selenovic, who's part of the Institute of Solar Nanotechnology. And this work has been really led by two of my students now, one who's now already a professor at University of Michigan, and David Bierman, who now also has now taken parts of this technology on to the incubator at Lawrence Berkeley National Labs at Cyclotron Road. So I mentioned kind of the idea behind solar thermophotovoltaics, but certainly while it seems very promising in nature, there are significant challenges, one of which is thinking about now if you want to tailor the spectrum to match that of a photovoltaic cell, the band gap of the photovoltaic cell, then you have to operate at relatively high temperatures. Right? So if you think about the thermal emission process, this typically will happen even in a low band gap type cell at least 1,000 degrees Celsius or so. Okay? So of course, with high temperature operation, there are challenges such as that of parasitic losses, and there are certainly spectral non-idealities that then get accentuated in this case. And so prior to what we've been pursuing, then certainly there have already been people working in this field. However, they've usually relied on kind of the intrinsic material properties, such as that of tungsten or silicon carbide, to help you kind of thermally emit to the PV cell. Also, because of these non-idealities and rely on the intrinsic material properties, then in fact you have to operate extremely high optical concentrations on the order about 4,000 or higher X in concentration, which can be relatively expensive when you think about all the optics that are required. Also, in addition to that, there still have been challenges that have led to efficiencies. While theoretically you can get over 80% or so, what's demonstrated experimentally has been less than about 1%. And so where we saw the opportunity is really kind of breaking down the system and thinking about a design that allowed us to understand what are the energy transport and loss mechanisms, and can we quantify them better such that we can create an experimental platform to demonstrate kind of what is possible with this type of what is possible with spectral control using these nanophotonics, as I'll get into on the next slide, but also think about how can we now kind of understand where the energy losses are going such that we can get higher and higher efficiencies to realize this type of system. So we started off with this platform as shown here. So what we have here experimentally is this planar type STPV configuration, where here the sunlight is coming in from the top here into the structure where this is your selective absorber emitter that's interfaced with your photovoltaic cell. What we decided to do in this case is now pattern this absorber structure that now tries to capture all of the light in the form of heat using a multi-walled carbon nanotube array, which is well known to have a very high emissivity or absorptivity close to 1. And what we've done here is that we played a trick with the geometry in a way. So we've taken now what we've defined as an area ratio, where we pattern a certain area with carbon nanotubes, such that we can have a relative area, a ratio of the area of the absorber or the emitter to that of the absorber. What we've done here is selectively try to pattern this such that we can kind of increase the amount of irradiance, the amount of sunlight onto this absorber, and such that it can essentially kind of overcome the emissive losses in this case. And what we've done in the background here is have now a low emissivity material in which we've used as tungsten. Okay, so working with this area ratio and being able to pattern this carbon nanotube array in a selective area, we've been able to get area ratios from about 1 to about 12 using this configuration. So now on the back side of this device, what we've done here is now utilized in collaboration, Marin Solicek's group, various type of photonic crystal designs. Okay, so in this case, we started off with this one-dimensional silicon dioxide photonic crystal, where it essentially has these layered type structures. So it's kind of a layered design that allows us to kind of control the constructive and destructive interference of light, that allows us then to target the PV cell in terms of the emission spectrum. So here what I'm showing you is the PV cell, the internal quantum efficiency of the PV, which is in purple. And then this is the emissivity based on your emitter structure. You can see here that we're targeting pretty well the band gap of the PV cell. And this way we can try to aim for really an efficient conversion via this kind of thermal emission process. So with this, what we've started to do is try to understand more in detail what is the role of this area ratio in this kind of planar design to help us understand better how do we push forward the efficiency of these devices. So our first studies were looking at, well, when we vary the area ratio, what happens? So what you're looking at here is a power output as a function of the irradiance, the solar irradiance. And on the right side here is the kind of the temperature of the absorber emitter structure that you're emitting kind of the photons with this tailored wavelength to the PV cell. Okay. So you can see here, as you increase the area ratio for a fixed temperature, you're essentially improving the efficiency, the thermal efficiency, okay, of the process. And the reason for that is you're increasing your irradiance such that it outpowers essentially the emissive losses. So your thermal efficiency in this case will continue to increase as a function of the area ratio, but you're increasing your radiance in this case to now maintain what the temperature is that's ideal for the emission to the PV cell. Okay? And so if you looked at then a fixed concentration, what you start to see that as you increase the area ratio, then your kind of thermal, your TPV conversion process will decrease. And that's expected because at some point you're going to be now operating at a lower kind of temperature such that it becomes not ideal for the PV cell, right? And so there are these kind of trade-offs and thinking about whether there certainly is an optimal point for a fixed concentration of this overall efficiency as you are now increasing your emitter to absorber area ratio. With this understanding, and what we started to look at is, well, we've been able to demonstrate with this platform now about 3.5% solar to electrical energy conversion. Okay, certainly that's still much lower than what was the theoretical limit, but also about 3x higher than what's been demonstrated previously. And we looked at specifically, well, where are we losing this energy, right, in this conversion process? And certainly because we were dealing with a relatively small size scale device, it's on the order about 1 by 1 centimeter, right, there's a lot of parasitic losses still from the supports and that of the sides and inactive area, for example. And certainly there's still, there's only a certain amount of energy that's hitting the PV cell. And in this process, we said, well, I think we could do better if we can think about, well, in fact, about, the amount of energy that's above the band gap is still only a portion of what is then also getting lost, right, below the band gap, right? And so what we've started to do is, well, can we think about, given the device that we have, how do we kind of take advantage of the energies that are below the band gap that are not useful for the conversion process itself? And so part of this process, what we've also studied is kind of looking at modeling and thinking about what is possible if we were just to scale up and improve some of these device design based on the understanding that we've obtained. And you can see here that, in fact, if we go from a 1 by 1 centimeter STPV device that I just showed you to that about a 10 by 10 centimeter device, in fact, you have significant potential even being able to exceed that of the Shockley-Quasar limit of these low band gap cells. What I forgot to mention is that we're using pretty specific cells in this case, where we're not using silicon cells, which are commonly used for the PV market right now. And part of it's because as you get to silicon, the band gap's higher. So in this case, you have to probably operate around 2,000 degrees Celsius. So as you get to these kind of, we're looking at these low band gap cells, kind of the limit of what we can kind of get to in terms of temperature, such that we can deal with a lot of kind of the contacts and measurements that are non-trivial as you get to higher and higher temperatures. So this is really the first step in thinking about it. And so we've been working on these indium gallium arsenide antimonide cells. But we believe as we scale up this device, there is significant potential. But with this study, we were able to say, well, certainly there are still a lot of losses. And so there's certain photons that are hitting the PV cell that still are not useful for the conversion process, and they get converted to waste heat, essentially. And so our next step was thinking about, well, how can we take advantage of those low band gap cells that are not being useful to the conversion process? I showed you this earlier here, this plot of the emission from the one-dimensional photonic crystal design as compared to that of the band gap of the cell. And what I didn't point out, although you probably saw, is that it's still this long tail that can lead to this kind of detrimental emission at the lower band gaps. So the idea here is, well, can we reflect those low energy photons and be able to then utilize them for emission then at higher temperatures, right? Again, or not at higher temperatures, but for emitting them at the wavelengths that are necessary for the conversion process. Right? So what we did here is we took advantage of a Renewable filter. This is the spectral, the reflectance as a function of the wavelength here. And this matches relatively well in terms of where we would like to kind of reflect the photons. And you can see here that by including this Renewable filter in this process, as I'll show you in the next slide, that we've been able to further improve the performance of these solar thermophotovoltaics. We also did a few other things. One of the challenges we faced is that the low band gap photovoltaic cells were not very high quality, and we were able to work with Lincoln Labs as a way to help us now further kind of improve some of the features of those fabricated cells, and also increase the device footprint to about 4x that. And with that, you certainly have less parasitic losses from the sides, and that also contributed to the improvement in efficiency. So with this test platform, what we've been able to do now is really do a direct comparison between that of what the conversion process with just that of a photovoltaic cell, and once we introduce the selective emitter absorber with this Renewable filter incorporated into a STPV system. And this is what we saw. So this is now looking at the device conversion efficiency as a function of the output power. And as expected, the photovoltaic conversion process is relatively constant. And with our kind of improved design, you can see here for different area ratios, I believe this one's about 8 and this one's 12 here. You can see that at this point there is a crossover such that, in fact, you can exceed the device conversion efficiency compared to that of a PV cell. Just for reference here, this is some of the earlier reported works from our group and collaborators. So we were very excited about this result because what this shows for the first time is that that, in fact, having this kind of spectral control using these nanophotonic device, selective absorber emitter structure, that in fact you can start to see that there is a spectral enhancement, right? So there's actually improvement because of this intermediate structure of this solar thermophotovoltaic. In addition to that, we were very excited about this result because, as expected, if you're now being able to use more effectively the photons that get converted to electricity, then thermal management should not be as much of an issue, right? So a lot of the photons that are generating heat are no longer generating that heat because they're actually useful for the conversion process. So you see here, this is a heat generated as a function of the output power density. And you can see that as you ink here's a PV cell in the dotted gray here, kind of a fit to the data here. And you can see here that from our STPVs, you can see that there's a relatively significant reduction in the heat generated from the cell itself. It's about 2x or so. And so certainly you can think about this device as more efficient in terms of the conversion process itself, but also thinking about how it reduces also the thermal load in this case. So it's effectively a thermal management strategy. So we've demonstrated now about an efficiency closer to about 7%. Again, we're still quite far from the theoretical limits. And we think there is a path forward in this case. And this is what I show you here, and looking at a plot again of the device conversion efficiency, assuming that we have an ideal kind of PV cell. So we're not working on specifically the PV itself yet. This is a function of the output power density. And what I show here in the dotted gray line here is what is the Shockley-Queisser limit, again. And when we have, what our work has shown based on these models is that with an idealized PV cell, that this is where we are in this curve, right? So certainly at some point we can reach kind of where we are in terms of the Shockley-Queisser limit. But this is also still a relatively small device, and we envision kind of a system such that we still scale up, say about a 400 centimeter square device. We can see that the crossover point for this scaled up STPV device is in the green here. And the crossover is about 1,000 degrees Celsius for the emitter with about 800x concentration. So we're still relatively reduced concentrations compared to what's been demonstrated before. And we can get to kind of efficiencies such that they become now competitive and thinking about this technology as deployable. So this is one example by which we've been working on and thinking about how we can take advantage of spectral control using these kind of nice kind of nanostructured materials, including these carbon nanotubes and that of these photonic crystal designs. And we've been paving kind of directions in further improving the designs and moving towards not just these one-dimensional layered structures, but also two-dimensional photonic crystals and other types of cavity type configurations that allow us to now further push this limit. So that's one example of some of the things that we've been working on. The other thing that I'd like to focus a little bit more on is specifically that of the solar thermal process. And we've been spending a lot of time in thinking about, well, how can we now improve the efficiencies of these solar thermal kind of conversion, concentrated, say, solar power plant designs, and to make them more efficient and lower cost such that they can be more deployable and maybe more competitive as we think about the trade-offs between solar photovoltaics and solar thermal. When we look at now kind of the internal workings of a solar thermal power plant, certainly when we think about the overall efficiencies, they're still pretty low. They're on the order about 10 to 15%. And the reason for that is there are multiple conversion processes along the way, from the sunlight to thermal via these collector fields. For example, what's shown here is a parabolic trough configuration. The solar to thermal conversion process is only about 55% efficient. And then from the thermal to electrical, using this steam cycle here, it's about 25% efficient. So collectively, that kind of amounts to this 10 to 15% in overall conversion efficiency. Certainly you can see from these kinds of systems also a lot of there are very costly components, such as the collector field itself and various kind of moving parts in these power these steam cycles. And so that's still a challenge in thinking about CSP or these solar thermal power plants in general. We've been focused on a few aspects of this problem and think about how do we push forward kind of various aspects of it and think about, well, trade-offs of kind of concentration. If you increase kind of the mirrors or change the types of mirrors that you use, then that potentially could decrease the cost. Or potentially think about other designs that don't utilize the same type of infrastructure, such as that of these evacuated tubes that then you have to operate in vacuum, and that can also lead to challenges and complexities in the system. So one of the things that we've been working on, and this is in collaboration with Gong Chen's group at MIT, has been looking at what we call these aerogel solar thermal receivers. And the idea with the aerogel, which they're common used in building materials, is that they're very good insulators, right? They're very good thermal insulators in this case. And what we've conceived of is an idea by which instead of just using the insulating properties of these aerogels, what we wanted to do is also make them optically transparent, such that sunlight can then can penetrate into this kind of receiver design, into these black tubes that then can effectively capture the heat. So we're using these optically transparent, thermally insulating aerogels, such that effectively we're creating a greenhouse. Right? And in this way, then we can trap the heat locally and heat up these tubes with minimizing the losses in this case due to radiation and convection as well. And the opportunity is the fact that these aerogels also don't have to operate in vacuum, right? If you can, in fact, conceive this design. And so, in fact, instead of using, say, a parabolic trough type configuration, then we can move to, say, linear Fresnel reflectors instead at lower concentrations and also facilitating potentially lower cost in this case. So we've been working on this for some time. And as I mentioned, the key idea here is that we would need to create these aerogels that are optically transparent. And traditionally, when you think about commercial aerogels, they usually have this kind of bluish tinge to it. Right? And it's because of the scattering of these kind of silica bead type structures, right? And what we've been working on then is really fine-tuning the structure itself and being able to control the distribution of these aerogel, of the pores of the aerogel, and to also decrease the size of the aerogels such that we can minimize scattering. So through the support of RBE, what we've been doing is, in fact, now being able to create what we call these optically transparent, thermally insulating aerogels that look almost just like soda-lime glass, right? They look, and you can see from the transmittance measurements as a function of wavelength, in fact, they're far superior to that of commercial type aerogels in this case. And meanwhile, what we've been able to do is still maintain the ultra-low thermal conductivity, less than about 0.1 watt per meter Kelvin, and demonstrated that they can be robust on the order of about 400 degrees Celsius, which is kind of the target we've been focused on such that we can drive a steam cycle. Okay? So with this kind of concept, one of my students, Lynn, while it's been certainly a large group effort on our both Gong, Chen, and my group's collaboration, is that we've been able to first start off taking advantage of these aerogel structures and been able to look at what is the potential of this type of aerogel, these optically transparent thermally insulating aerogels, right, in terms of using a black body type surface and being able to just put the OTTI, the aerogel on top of it and look at, well, what's the temperature that we can reach, right, with no concentration at all. Right. So this is, so the experiment that we set up is just using black paint, using a pyromark paint. The absorbance is typically, the solar absorbance on the order about 0.97 and thermal emittance is about 0.8 to 0.9 or so. And again, we're constructing this without any vacuum, so it's just in air. What we've done to now insulate the rest of it is just a conventional kind of low-cost insulation for the non-active area. And these are results from the experiments which show a lot of promise. So here, what you're showing here is a temperature response, right, as a function of, so it's a temperature as a function of time. This is an ambient here. This is in a controlled environment in a lab first. And you can see here that while the aerogel surface, you can see the aerogel surface is still relatively low here, but meanwhile, the absorber surface is reaching relatively high temperatures, over exceeding that of about 220 or so degrees Celsius, right? And what we've been able to also show is that we can reach stagnation temperatures. So here is a stagnation temperature, as a function of the aerogel thickness. So as you obviously increase the thickness of the aerogel, there could be trade-offs in terms of the transparency of the aerogel, but also improving kind of the insulation properties as well. And we've been able to now, as we increase the thickness of the aerogels, reach up to even greater than about 250 degrees or so. And so this has been really exciting. Imagine this is just with one sun, right? And without any vacuum or selective surface. And if you compare it to what's been demonstrated with the vacuums, it's very difficult to even reach this at relatively low cost. So we've been excited about these kinds of material sets that we've been able to create using these optically transparent thermally insulating aerogels, and we've been able to now demonstrate it in an outdoor setting. This is, in fact, during the winter, cold winter day, although sunny, in Boston on a rooftop. You can see the ambient is pretty much close to zero. And so from this kind of prototype that we've now faced towards the sun, you can see that, in fact, here's again, the temperature is in blue. Here's the solar flux measured, and here's the ambient, right? So you can see that, in fact, upon solar exposure, you can reach over about 200 degrees Celsius. Right, about even that of 220 degrees maximum temperature. And so this suggests that there is significant promise in this, in taking advantage now of being able to finally tailor these kind of nanostructured materials, in this case, these aerogels, in a way to help us now achieve really high temperatures. What we've been moving forward towards is not just, of course, demonstrating this at a single sun, but think about, again, the ultimate goal is thinking about, well, can we deploy these in a solar field type configuration with linear Fresnel? And so recently, we spent quite a bit of time in being able to do an actual real demonstration, or more kind of larger scale demonstration of this using a linear Fresnel array that we've constructed at a Bates Center close to MIT. And here's a picture, you can barely see it because of the contrast, unfortunately, of a receiver design that tiles a whole bunch of these aerogels into about a 1 meter squared, or 1 meter long area, about a foot in this other direction, and so we'll be able to create this kind of receiver design and actually test the performance once you start to concentrate using this linear Fresnel setup. And these are results that suggest significant promise in this. This is looking at the efficiency as a function of the temperature. And the blue dots are that of the data that we've obtained from these measurements. You can see here from our modeling that we have very good agreement in terms of what is possible in terms of the thermal efficiency and also that of the exergetic efficiency that's modeled and also measured. You can see here, though, what we were pushing towards is getting higher and higher temperatures such that we can get even higher efficiency levels, which was kind of one of the milestones of the ARPA-E project. Fortunately, this is still kind of in progress because of some challenges we face with some of the piping since we were delivering now oil into this infrastructure, and that made some of the kind of the measurements much more challenging than anticipated. But what I want to show you here is really the opportunity space in thinking about, well, if we can advance these kinds of materials, right, and think about extending beyond what we know about kind of these insulators that are excellent, but also now pushing the optical properties such that we can realize these kind of other types of designs. Certainly, there's also, as I showed you this picture, a lot of opportunities in also thinking about this other side of the system. The steam cycle has been kind of developed for many, many years, right? And certainly, still there are opportunities in thinking about how do we better, how do we achieve higher efficiencies based on this kind of thermal to electrical conversion process. And a lot of it has to do with liquid to vapor phase change. And a lot of my work in the past has been focused on this aspect of how do we enhance kind of this liquid to vapor phase change process such that we can now potentially improve the efficiency of this cycle. I just thought I'd show you a little bit about this since, for the sake of time, I don't have a lot of time to get into this, is that we focused a lot in thinking about, well, how do we take advantage of various types of structures such that we can now further enhance the heat transfer associated with the phase change. What I show you here on the left is some work done by my former student, Yang Zhu, who's actually in the audience. She's now a postdoc with Yi-Tui's group at Stanford. And she led a lot of the work and thinking about, well, if we incorporate, what we're seeing here is channel type configurations when heat is applied from the backside. And trying to understand that, in fact, when we have these kind of channel type configurations, undergoing phase change from liquid to vapor, say, how does that affect kind of the flow patterns and the temperature? As you see here from the top is that when you don't kind of pattern the surface with any type of features, you have a lot of kind of instabilities from the flow that can lead to local dry out, which becomes detrimental in a lot of these kind of liquid to vapor phase change processes. And what she's shown is that if you incorporate various types of structures onto the backside of this now system, then in fact you can improve stability significantly in this case. And that could allow us to manipulate better that liquid to vapor phase transition. We've also shown through time the video is shown on the right, is in fact, we can in fact control much better liquid to vapor phase change. And we can turn that process on and off by being able to take advantage of charged surfactants that adsorb onto interfaces such that when you apply an electric field, you can control locally where that boiling in fact occurs. The idea here is that what you're doing is really locally changing at the surface level kind of the hydrophobicity or the hydrophilicity of the surface. And that can effectively control the nucleation of these bubbles and then also effectively the heat transfer coefficient. Now, what I show on the other side of things is that of condensation. So during these kind of steam cycles, you need to now change phase from liquid to vapor and then back from vapor to liquid. And in fact, condensation can be a relatively important process in these steam cycles and thinking about also water management as well as also the efficiency of the overall system. So we spent a lot of time also looking at, well, how can we control the kind of condensation process such that it can facilitate kind of enhanced heat transfer via condensation. And we've studied a lot about morphology of these kind of droplets as now they nucleate from the vapor phase into the liquid phase and create these kind of droplets. And also, can we now promote new kind of methods to condense liquids? What I show you here, although it's a little bit dark here, is that showing kind of on these kind of structured surfaces, these are copper oxide nanostructures, we can coat them with a hydrophobic coating and then promote what we call jumping droplet condensation. So you can barely see it here, but it almost looks like rain. What we're doing here is taking advantage of kind of surface tension-based effects that allow for coalescence of these droplets and allow them to kind of shed off the surface. And in this way, because you have kind of removal of these droplets at much smaller length scales, you can in fact get much higher kind of heat transfer coefficients in this process. So I thought I'd just give you kind of a short overview of some of the work that we've been doing in that area. And certainly there's more that can be done. And of course, kind of getting it into a steam cycle also requires a lot of kind of considerations of reliability as well and manufacturing of these kind of structures onto these surfaces. But I thought I kind of, in the last kind of 5 minutes or so, I thought I'd share with you some more recent work that we've done, also thinking about kind of the intersection between energy and water. Living in California, you probably know that one of the big challenges we face is water shortages in a lot of different areas, and we have certainly droughts, maybe not as much in the Bay Area, but certainly down in Southern California, which is where I grew up. And this is a mapping showing that, in fact, kind of significant water shortage in a lot of places in the world, where in certain areas you can see that, in fact, the whole year they really don't have water, right? And that becomes a significant challenge and think about, well, and especially in areas which are developing, right? They don't even have the infrastructure to, say, use technologies such as reverse osmosis or multi-stage flash. And so we've been thinking a lot about this problem, and actually the opportunity space kind of emerged from also another ARPA-E project working on something very different. But we were thinking about this idea in that while there's certainly a lot of water shortage, there's also a lot of abundance of water in our atmosphere. And when we think about the amount of water in the air, it's equivalent to about 13,000 trillion liters, right? So certainly that's a lot of water, but how do we actually harvest that so to provide the drinking water that we need in the world? And so we've been thinking about, well, how can we develop a device that we can harvest water from the air? And certainly this is not an area that hasn't been pursued in the past. One of the most common technologies is known as dewing. So the idea here essentially is you have this kind of refrigeration cycle, right? So you essentially get below the dew point of, and once you get below the dew point, then you can condense the water, right? So you can imagine here that when you look at the thermal efficiency, which is defined as a harvest of water over the input energy as a function of the relative humidity, that there are conditions such that it makes kind of dewing infeasible, right? So if the humidity levels are so low, it becomes so energy intensive that it really becomes not possible. So really dewing technology serves a unique kind of space where in some places with high relative humidity, then they could be very well suited and relatively efficient. What we've been targeting is actually the low humidity range, right? In often cases where there are arid climates and there's also the very limited infrastructure in those areas, can we develop technology that can then harvest water from the air? And this is where we've been working with Omar Yagi's group at Berkeley, where we've been developing this new water harvesting technology that's based on adsorption. What I show you here is exactly first how the device works. So the idea here is by taking advantage of a new material set known as metal organic frameworks, or MOFs. And the idea here is that if you have this kind of material in this device, you can in fact capture a lot of the water. It acts like a sponge and absorbs this water onto this material, these metal organic frameworks. And because of the unique properties, as I'll get more into about these MOFs, is that you can release them relatively easily if you apply a small amount of heat. So you can apply sunlight in the form of heat again to release these water molecules that are adsorbed onto this material and now allow you to now form locally an environment that has relatively high humidity, nearly 100%, such that you can condense this water near ambient conditions, right? So instead, you don't actually have to use refrigeration to, in fact, allow for this water harvesting. And so the key here is, of course, is the material set. While the concept seems relatively straightforward, my student here really led this effort here, working with Omar's students, and think about, well, how can we take advantage of really these metal organic frameworks that have a unique kind of characteristic? What I'm showing here is an isotherm. This is a water uptake as a function of the relative humidity. And there are certainly different types of what they call isotherms of these various types of adsorbent materials. And because we were interested in the low relative humidity range, we were interested in being able to look at the isotherms and looking at how we can capture water when there's a nice sharp step, say on the order about 20% relative humidity or so. So we were focused on these metal organic frameworks with this sharp step because not only does this allow us to capture the vapor, the water vapor, at these low humidity ranges, also allows easy release because of this really the steepness of the isotherm. And so being able to incorporate these metal organic frameworks have been kind of a process by which we've been able to not only characterize the material itself, but being able to now optimize the characteristics and consider the heat and mass transport processes in this material set and characterize them at the lab type level in a layer type structure before we've now been able to develop a device. I won't get into the details looking at the time, but the key here is that we've been able to then integrate this based on the optimizations. And the heat and mass transport, in fact, is very important in these designs. And think about how we can optimize the amount of time for the adsorption process as well as the desorption using sunlight. So it becomes powered really by no extra electricity, right? External source of electricity. So what we show here is a prototype that we first tested. And this was done just on an MIT rooftop. And what you see here is this single layer of this metal organic framework that's impregnated in a copper foam matrix. And the reason for that is because we needed to have something that has a relatively good thermal conductivity, but metal organic frameworks don't have intrinsically a good thermal conductivity. So that allows us to enhance kind of the heat transport when we're kind of facilitating the absorption process. And so here, and the desorption process, I should say. And what we've done here is incorporate it into this matrix and then just have essentially a box that we've designed such that we can now shine sunlight with an absorber on it that then heats up this layer. And once it absorbs enough, once it's kind of captured the amount of water vapor onto, or saturated it in this case, you can release it and you can create, you can see that in fact you're condensing water in this case, and you can eventually collect that. Our initial design, we used still a pretty elaborate setup where while we claimed that we can do this passively, initially we focused on having much more controlled environments. So we used a thermoelectric cooler. But what we've moved forward towards is not only just demonstrating this design, is that we've been able to move forward and think about, well, can we do this more practically and also demonstrate it in a place, in a climate where the relative humidity is low. So we moved forward to that of taking this kind of design to Arizona with a few improvements. And the key here is in this kind of more arid condition that the nighttime humidity is about 20 to 40%, and the daytime still is relatively low. And the key here is also that the dew point can be relatively low and even negative in this case, right? So this becomes very challenging for that of the dew harvesting type technologies. What we've been working on is then kind of an optimization of that process I showed you earlier and being able to now do a few improvements, one of which is to kind of further kind of capture the amount of heat from the solar, from the sunlight itself by incorporating that same aerogel that we fabricated earlier, being able to better insulate but then allow for kind of a great solar transmission, right? And then also then using air-cooled design instead of using a thermoelectric cooler and a few other things that I won't get into in detail to be able to now further kind of demonstrate the promise of this technology and actually take it to this Arizona condition where the humidity is low, right? And this is the kind of the opportunity space that we found. Here is a video just showing you this process. You can see that immediately what happens in this kind of, once you expose this device with the sunlight, the form of heat, is that you first immediately see the whole kind of viewport fog up, which suggests that it's condensing, right? But then as the system's heating up, then of course, then you start to see kind of the fog disappear. And so in this case, we've been able to show that this kind of device is operational. We've taken data and being able to show kind of what is a kind of monitoring the temperature as a function of time for the case when we're first adsorbing and then now desorbing once we expose it to the sunlight. Because we're still dealing with relatively small portions or small quantities of this metal organic framework, we weren't able to actually capture the amount of water from the surface. And so we've been able to take advantage of simulations in a way to help us now quantify the amount of water we've been able to capture. And what this suggests is that we've been able to get about 0.3 liters per about kilogram of this metal organic framework. And certainly there's still a lot of opportunity space in there, and that being able to further tailor these materials, which are still not optimal potentially, depending on where, what the conditions are, and also how to further now scale up this device in a way such that it can be kind of delivering, say, on the order of a family size unit, say 15 liters or so. We anticipate, say, a design of about a 30-liter, maybe like a suitcase size type system to deliver that 15 liters of water for a family. So what I show you today are just a few examples of the types of things that we've been doing at the intersection of kind of novel materials and functionalities of the materials to address certain challenges we face in the energy and water space. There still is a lot of room in terms of what we need to do to really make it kind of advance further technology and bring it kind of to the world. And we think the first is that we certainly can improve the performance by being able to tailor further kind of the nanostructure materials, think about how we could scale up some of these materials. The metal organic frameworks are very promising, but also face challenges in scale up right now at a reasonable cost. there's also kind of robustness concerns when we think about these types of material sets and how do they sustain these harsh conditions, say, in a steam environment, and further kind of improve the performance over time. So what I show you is just a few examples of tailoring these structures at the more smaller scale, but certainly, hopefully, you'll see there are opportunities in being able to address kind of these large energy and water challenges. So with that, I wanted to acknowledge my wonderful collaborators and my research group that really has carried on this work. I've also been very lucky to have a lot of great support from various agencies through the years to be able to kind of carry on the various efforts in my group. So I know I'm out of time, so I'm happy to take any questions at this time. Thank you.
Thanks for that so much, Professor Wang. I felt like we got at least 3 or 4 dynamite talks all rolled into one, thanks to your integrating together within a common technology framework. So let's take some questions now, students.
So what's the material of the thermo-insulating aerogel and how to make it in a high throughput and low cost?
Sure. Yeah, that's a really good question. So sorry if I didn't say it. We're dealing with silica aerogels. So it's silica structures. And the way we do it, it's a sol gel process, and it's the key step is a critical point drying to get it to tailor the size and the distribution, right? So we've really fine-tuned the recipes to be able to really get that to achieve the optical transparencies. And so certainly that becomes an issue when you think about kind of cost and because it's kind of a serial process, right? You have to kind of put it into the critical point dryer. But we've done some cost analysis based on the work from the RPE grant. And we anticipate the aerogel itself is about $100 per meter squared or so. And at that cost, we believe it can, depending on the application, it can be competitive to kind of existing vacuum tube type receiver designs. So certainly we are looking into other processes as well when you're thinking about how to further scale up, because what we can do right now, I mentioned we had to tile these aerogels because of the scale of our critical point dryer. And so what we're interested in doing is thinking about, well, certainly you can buy bigger critical point dryers, but there are other processes that you can use for that last step. And there's ambient drying techniques, although there are trade-offs because of the control and the kind of capillarity kind of having a challenge with some of the sizes that we want in the distribution. So we're still pursuing those avenues, but we think that given what we've demonstrated so far, that if we can say, kind of think about what are the right markets, that this still could be kind of viable for those markets.
Other questions?
What is the condenser material and structure for harvesting water from air?
Sure. It's just a simple condenser design. There's no kind of special material. So, for example, we can use aluminum or a copper or a metal that interfaces with this air-cooled heatsink. Right. So right now, that's not kind of the critical element that kind of there's no novelty per se in the actual condenser of these the water harvesting device. Certainly, there could be kind of some things we could integrate that could potentially improve kind of the efficiency as we push further the design. But right now, we haven't really focused on that. So we could start thinking about these kind of enhanced structures, surfaces, and how that could potentially kind of further enhance the heat transfer.
Over on the left side.
You mentioned in your science paper that you could get 3 liters of water per kilogram of the MOF. And I'm wondering, but you said here that you could get 0.3 kilograms.
Yeah, so I didn't mention the subtlety. So with our first science paper, we talked about how we could get that 3 liters, and that goes to cycling, right? So if you cycle, say, 5-6 times a day, you can get that 3 liters, right? The challenge with these very arid climates is that you're actually limited by your absorption process overnight. And so it's the heat and mass transport that limits how much water you can actually capture through, say, the duration of the night. And so that becomes a very challenging proposition. And so because you can't cycle as much, because you're limited by the heat and mass transfer. But I would say that's not the limit, right? I think there could be some design considerations of the materials aspect in terms of the kinetics of that, as well as also how you design the kind of I mentioned we use a foam right now in terms of what you do to incorporate these metal organic frameworks. So there's still opportunity space there, I think, to pursue further.
Alex, and then back up. Alex.
I have a basic question. So we still only get a kilowatt per square meter of solar energy coming in for any of these deals. Are you aware of the paper, I think it was in Science not long ago, that studied the relative use of desert for solar thermal or PV in terms of reducing carbon emissions? That the desert unbulldozed with no PV, no thermal solar, actually absorbs more CO2 than that power that could have been generated and produces and prevents emission. And the reason for that is because desert plants must have very deep roots and very extensive root systems to survive. And that carbon storage then is destroyed when we build things like Ivan down south and so forth, which don't really work. I mean, it actually charges, it makes electricity for 8 times what we make it elsewhere. So I'm trying to get a picture of, this is an environmental issue that we're facing of most serious proportion. And so I think anything that we're researching, we should actually look broader beyond the things that your students are enjoying and getting a lot of it. Education out of it, but there's a bigger picture. And I don't often see that bigger picture in all these various research projects. And in particular, you can't drink the water that you're harvesting and live. You have to do what people in the Caribbean do who collect rainwater. They take pills, mineral pills, because you can't live on pure water.
Sure. Certainly. I think
So
you
where
bring
does
up
that fit in, you know?
yeah, you bring up a very good point. I think I think we need to consider both sides of it, right? And I think you're right. This is more of the technological front, and certainly there are certainly opportunities, as you mentioned, that we need to consider when we think about just energy kind of landscape and how much we utilize, say, even in a household for heating and cooling. And I know there are metrics by which you would save if you just kind of didn't use central air, right? For there certainly you could save a lot, and the human kind of the habit is also important, right? In terms of how we think about the energy landscape. And
our politicians don't bother to study things.
certainly.
Before they pass them.
Yep, absolutely. And so I think there's a balance of a lot of this, and you do bring a very good point, though.
Yeah, there was a bit of a research theme in the Tomcat Center for Energy Sustainability that tried to look at this the two sides of it. So I think I can actually tell you a little bit about that. But I think there's a lot of good potential synergies here as well. Back up there for the last question.
Is there a potential market for electricity in arid areas by your water from the air? And do you have any, from your Tempe, Arizona experiments, any estimates of kilowatt hours per 100 cubic feet of water or anything like that?
Just so I understand your question, you mentioned about electricity locally to be able to
Use electricity to generate water from the air.
I see. So, so this technology is intended not to try to utilize electricity to power it, right? So we're trying to push towards a system by which we're just using sunlight in the form of heat, right? So, and so certainly, in terms of electricity, I think it depends on where we are, and we did not really examine that, I would say, in Tempe, Arizona, because the idea here was to really try to power it passively. There have been systems, I would say, we are aware of one company that has been kind of pursuing technology in this space, and they've been looking at solar PV powered units. Right, and so that's kind of the other option that people have been pursuing in this kind of absorption-based approach. But we're hoping to design a system that really can be passive in nature. And that will depend on a few things in terms of also the size of the unit. I think as you get to more village type levels, I think the design will have to maybe change such that if once you have stacked type arrays, that may dictate what we need to actually get this to work, which may then require some electricity.
Great. I see we're now just about out of time. So I'd like to thank Professor Wang one last time.
Great. Thank you.
fantastic talk.